our labs are going to be on not Wednesdays, Tuesdays, excuse me. And I have an office after our lab. Our lab meets 9:45 to 12:55, same hours. And so we'll have a short one, 12:50 to 1:15. Also have an evening lab that ends at 5:40, so 5:40 to 6:30. And then Wednesdays, our lectures are short by 5 minutes, and so it'll end on Wednesdays at 12:50. And so I have some short office hours there. For the location, it's going to be either in this room or lab, which is 164, just down the hall. Oh, this is 120 is my office, and 108 is right across the hallway here. 108 is the computer lab, so sometimes we'll have office hours there. All right, so this is the dictionary definition. This is what we're doing in Chem 4. We're studying chemistry. And what is chemistry? Chemistry, I like definition number 3 here. No, actually, no, not definition number 3. Make that definition number 2. The composition, structure, properties, and reactions of a substance. But I would rather change this a little bit. I'd modify this to be the composition, that is, what is it made of? What is what made of? A substance? We don't always study substances. Sometimes we study things called mixtures. And what's the difference between a substance and mixture? So we'll talk about that this week. And so rather than narrowing it, this is too narrow for me. I want to know the composition, not only of mixtures, but of more complex systems as well. And so I'll just call this matter, because matter, do you know what matter is?
Anything, everything?
Yeah, it's pretty much not anything. There are some things that aren't considered matter. Do you know what a couple of things that are not considered matter? Like maybe 2 things that aren't considered matter that.
Oxygen.
Well, oxygen is actually, even though we can't see it, there's oxygen present in a lot of things, like rust. Rust has a lot of oxygen in it. There's oxygen that we breathe. This room contains 20% oxygen, roughly, a little more than 20% oxygen. And it's considered matter because, you can feel it. If you move your hands back and forth, you can feel the air in this room. It's there. Matter is everything except 2 major ones.
I'm thinking like ideas and thoughts, maybe.
Yeah, probably ideas and thoughts. Okay, that wouldn't be considered matter, I'm sure, but more like physical type. Well, tangible in the sense that it's there, but not tangible in the sense. Well, I suppose you could kind of package it up and store it in certain ways. Yeah.
Is it on the planet?
Yeah. Well, it's but one of them is not really on the planet. It's people have been trying to get it on the planet, but having a very hard time achieving it on the planet.
Is it like dark energy?
In a way, it's kind of related to dark energy, but in general, it could just be energy. Energy is one that's not really considered matter, and there's one other that's considered matter. What would that not matter? Do you know what that would be? Well, we'll just encompass the whole thing in energy. I guess the dark. I depends. There's dark matter. Although there's been some stuff written about dark matter recently. Does it exist?
What is dark matter?
Well, there's some discrepancy between numbers, and so they came up with this thing, dark matter, to reconcile the numbers. I guess it's a little more complex than that, but there's a lot of dark matter in the universe in order for the numbers to match up in terms of mass, energy, this kind of thing. And so, but we are not going to be studying that. We're going to be studying the definition of matter is, does anybody know the definition of matter? Matter is like anything that occupies space. Then there's one other requirement, and it has to take up, it has to have mass. And so it occupies space and has mass.
Is light matter?
No, light wouldn't be considered matter because of the mass part of it. Light would be considered energy. But chemists study light. Chemists study light because it interacts with matter. And so matter is one thing that doesn't fall into that definition would be a vacuum. You know what a vacuum is? Like a perfect vacuum is empty space. Empty space could still have, fields, like energy fields in it, but it wouldn't have like mass. It wouldn't have matter in there. And so here we probably would modify this. The composition, that is, what is it made of? The structure, how are the components of that arranged? And the properties. Properties is how it behaves. Normally when we think of properties, there are two types of properties that come up. For chemists, we can just call those properties in general. But when we get into properties, we like to divide properties into two classes of properties. One class of the physical properties. Physical properties would be things like hardness, or state, is this solid, liquid, or gas? Melting point, that type of stuff. Density. Can you think of any others? Physical properties?
The absolute The absolute thing you just mentioned.
And the other type of property would be chemical properties. We're going to have physical and chemical properties. What's the difference between a physical property and a chemical property?
Physical, you can see, chemical, you can't see. Or chemical,
Well, actually, you can see both.
Is chemical like, does it not have like a melting point or something?
No, it could have a melting point, but we wouldn't consider a melting point a chemical property. We'd consider it a physical property. And the reason is, like when you melt something and then freeze it, do you get back the same thing? Yeah. If you get back the same thing, then its chemical identity hasn't changed. It's still the same type of matter, same what we call substance. But a chemical property, an example of that would be like burning. If you burn a piece of paper and then try to reverse it, are you going to get the paper back? No, you're just going to have ash or something. And so the identity, that is what the substance that was, or substances that was, has changed. And so in chemical properties, there's a change in the type of matter. Well, they do that in a different way because we call that reactions, like burning is a reaction. And so the other modification I'd make to this is I'd say the composition, structure, and properties, both physical properties and chemical properties. Chemical properties are under this, reactions here of matter, I'd say. And then that would be pretty good. Let's look at definition number one, the science of the composition, structure, properties, and reactions of matter. Here, I wouldn't divide, here, obviously, they must be talking about physical properties because, chemical properties are the reactions. And so we would call this physical properties. and reactions or physical properties and chemical properties of matter, especially of atomic and molecular systems. So that's okay too. All right, the course descriptions here. It's a 5-unit course. 5-unit course, you have to make sure you have enough time for this because there's a lot of memorization in chem, nomenclature, this type of stuff. And that takes a lot of time. There's a lot of reading, a lot of homework. So make sure you have plenty of time for this. Because not only are you spending a lot of time in class, you have to spend a lot of time outside of class studying chem as well. This course introduces the principles of chemistry, modern concepts of atomic structure and periodicity as a basis for understanding bonding, chemical formulas, chemical equations, and chemical reactions, states of matter, important elements and their compounds, solutions, acid-base theories, and reactions, net ionic equations, oxidation, reduction, kinetics, and chemical equilibrium, chemical nomenclature, and calculations. In the laboratory, emphasis is on observations, measurements, and elementary quantitative experiments, and introduction to qualitative analysis. So this is the course in a nutshell. The course objective, you can read through that. And then we're required to have these SLOs. SLOs are these student learning outcomes. These are 2 of our SLOs. We don't have that many published. But this is one with naming. Naming we call nomenclature, and predicting reactions. We'll talk about that later. This is a safety rule, safety goggles. You'll need these for lab. You won't need these until we get to a wet lab. They sell these at the bookstore. I think we also have extra pairs that were left behind after COVID. They weren't reclaimed, so we've been giving those away. If you need a free pair of used goggles, you can probably get them in the stock room. The required materials are the textbook. I put down the 6th or the 7th edition here. They did make a change. There wasn't much of a change between the 5th and the 6th edition. But between the 6th and 7th edition, they added one section, like a general interest section at the beginning of the chapter. And they added a few more homework problems. The problem is it's an expensive book. So I normally the publisher gives me a copy of it, but I requested a copy last year and I still haven't received a copy. So I finally broke down and bought a copy. It's over $300. I know it's expensive. So there are other options there. You could do the e-text, which is a lot cheaper. And I have the e-text of the 6th edition. I have the PowerPoints of the 6th edition, but they haven't given me access to the 7th edition yet. So I need to modify the homework I have posted on Canvas. I just need to change the numbers. The problems are all the same. They didn't change the content of those. I just got to get the correct numbers out. So be aware of that. If you already started looking at the homework, the numbers might not match. So I need to fix that. All right, this is not that expensive. This is the lab manual and supplement called the Chemistry 4 Supplement and Lab Manual. And there's a 2019 version. I was just in the bookstore, and so this is available. This one is reasonable, the price. And so it would be cheaper just to buy it than to print it out, probably. Or you might find the electronic version of this somewhere.
Are assignments turned in online or in person?
On both. Some are turned online, some are turned in person. So the question was, are the assignments turned in online or in person? So I'll announce which way it goes. For those that are turned online, I prefer it in PDF format. And so if you have something like Genius Scan or one of those apps, it's what you're going to use. If you don't, you'll need to get it. If you turn it in as a like a GIF or JPEG or something like that, sometimes I have trouble opening those fine formats. You probably have a calculator already. I recommend getting a calculator that has equation solver function built in. And so, as far as calculators go, you'll have the cheapest one. I don't know what the cheapest one. It used to be like $10. The one with equation solver is like the next level up, which would be like a $15 calculator. But that was the last time I purchased it. It might be more. I'm not sure how much more. Maybe like $20 now. The calculator I have, and you could use whatever. I mean, TI has these calculators, but this is the calculator I have. I just bought it at Target. It's a calculator FX115EF. Oh, okay. $17. Around $15. This is a pretty good calculator. And if you're continuing in chemistry to Chem 1B, you have to do a lot of quadratic equations. And this one has a quadratic equation solver to make those calculations less tedious. Well, faster. So if you don't have a calculator, pay a little bit extra and get something like that. All right. I'd also like you to get this quad-ruled composition notebook. These are like $2 or $3 from the office supply stores. Our bookstore used to carry these too, a little larger format. Quad rule just means graph paper rule. That's preferred. If you can't find graph paper, then college rule is fine. But just a composition notebook with a sewn binding. It has to have a sewn binding. The reason is for this for lab, we need like a permanent record. And if it's spiral bound or if it has tear out sheets, that's not considered a permanent record. It has to have some kind of permanent binding to be considered a permanent record. And so this is going to be for your lab data.
Is there like a size you prefer?
It doesn't matter, any size. The safety goggles, watch out because you might have some safety goggles at home, but if they have ventilation holes, then those aren't considered splash protection. We need something that seals, on the bridge of your nose and around your cheeks for splashes, upward splashes. And so that's why these are recommended. And we only have one kind, and that's the visor goggles because these fit the most people. And these fit over glasses as well. Some optional materials that you might consider getting, like a Sharpie pen. We'll have some, but if you want your own, they're quite handy for labeling things. We label glassware. We like to just write on the glass itself, and it's easy to erase. You can write. A lab coat or apron. You can get these. The purpose is just to protect your clothing. It's not necessarily to protect you from fire. At UCLA, now they require cotton lab coats, 100% cotton lab coats, because those will have some fire resistance in there, but they're expensive. The lab coat I purchased recently, I just got it off Amazon. It was about $15. It's nice to have. Here it's optional. At UCLA it's mandatory, and 100% cotton is mandatory. Also, gloves are mandatory at UCLA, and they require nitrile gloves. Nitrile gloves have much better chemical resistance than latex gloves. But either latex or nitrile are nice to have for some of the labs. All right, the required assignments, we're going to have midterms. Those are required, of course. The labs and lab reports are required. The labs, for example, at UCLA are a separate class. Here, they're together. They're combined in one class. And because of that, we have an articulation agreement that states that if you don't pass lab, that is, if you have excessive absences in lab or you have a lot of missing lab reports, and you don't meet the minimum requirements, although it's only 120 points here, some people just blow off lab entirely. Well, if you blow off lab entirely, you're not going to pass this class, no matter how well you're doing on the midterms. And that's because of our articulation agreement. And so you need to pass the lab in order to pass the class. But we'll have these midterms, it's 400 points, 4 midterms, each midterm worth 100. We'll have 10 labs. The reports are going to be worth 12 points each, so it's 120. Homework, these are 5 points each, 18 of those. A lot of chapters we're covering. And we aren't covering all the chapters in the book. I think there are 22 chapters in the book. We're going to have quizzes. Actually, I'm probably going to change this number here from 30. This is probably going to go up here, which will change the total points here. The final is going to be 160 points. And so the total points will be around 800.
Is the final a cumulative or just?
Cumulative, yeah. Is the final cumulative? It's going to be cumulative. It's going to cover the material from the beginning to the end. That's good to get confirmation because once, when I was a student at UCLA, I missed a class. So I asked the person next to me, is the final going to be cumulative or is it just going to cover the second half of the class? And he told me it's going to be cumulative. So I studied everything from the beginning to the end. It turned out, do you know what? The final only covered the second half of the class. So I spent all that time studying the first half and it turned out to be a waste of time.
Are we no longer using notes on the final exam?
No. The final exam is going to be closed note. Regardless of what the total points are, here the grade is just based on percentage of total points. And so this might change a little bit. But if you have 90% and above, that's an A. The cutoff for a B is 80. The cutoff for a C is 65. And so the C cutoff is a bit wider range here. The D's to 55 and 54 and below would be an F. The percentages might change a little bit depending on how hard the exams are. Okay, we have a special resources center, so if you need special testing accommodations or whatever else, you'll have to make arrangements with them, and then I have to work with them to get the exam over there and get you set up. Any changes, I'll just announce in class most of the time, or post on Canvas. All right, a note on cheating here. Academic honesty is mandatory. So, if you need help, here's some resources here. We have this Chem study room here. This Chem study room is Chem 106, which is across the hall over here. In Chem 106, there are some textbooks. Sometimes when you're reading our textbook, it doesn't quite click. It doesn't quite make sense. So what you might want to do is you look for an alternate textbook And the alternative textbook could be the same level, like Chem 4. But what I usually do is I look for the next course, like the next level. Because normally in Chem 4, they don't go into detailed explanation of certain things. But if you grab the Chem 1A textbook, they probably go in more depth. And when they go in more depth, it might be easier to understand. And so there are a whole bunch of other books over there. There should be a whole bunch of other books there, unless somebody threw them away. But are you familiar with the MESA program here, number 2? They usually have a facilitator there, and it's free, and there's no long-term commitment there. And so once they have that sorted out, I'll let you know here. And then there's free tutoring in the library, so you can check that out as well. Our book has a website called OWL, and there's resources there as well. The publisher is Cengage, so if you go to cengage.com, you can find some other things there. I think they're practice quizzes and other stuff. This is Cengage here. All right, any questions from that? All right, let's take a look at the syllabus. This is also posted on that link. I already have this up, so take a look at this. So we just meet Monday, Tuesdays, and Wednesdays. Tuesdays are lab days. So I have the labs. We're going to start lab tomorrow, but this is a short lab. And you don't need safety goggles for this particular lab. And you don't even need the lab manual necessarily for this one. So you'll have a little bit of time to get it. Once we get to experiment 2, then this is a much more involved lab. Okay. All right, so the schedule, we're just going to go through the chapters in order. So 1, 2, 3, all the way to, we're ending the semester on chapter 19. And we're not skipping any except 20, 21, 22. And so we're covering 19 chapters in 16 weeks. Chapter 1 is very short, Intro to Chemistry. Chapter 2 is a bit longer, Chapter 3. So we'll have to go more than one chapter a week. The reading for chemistry is pretty slow. Once you start reading it, it's not like you're reading fiction or something that 1,000 pages you probably can crank through. For chemistry, it's slow going because of calculations and other stuff that you have to look at. Chapter 1's short, though. So take a look at that one. We have some holidays, so we're going to be missing 2 Mondays here. Washington's Day and Memorial Day here. We have spring break here between, starts April 8th, so we'll miss this entire week here. The labs look like they're going to go in order, numerical order here, 1, 2, 3, but we don't. We're not doing all the labs, so we're going to have this exercise A as a paper lab. And then we're skipping 4 here, jumping to 5, 6, and 7. We're not going to do these 5, 6, and 7. We're not going to do those labs entirely. That is all the parts. I'm going to slim it down so we can finish it. And then we're throwing in 12 here. This was supposed to be 5, 6, 7, and 12. I made a mistake with that. And so that's 4 labs and 2 lab periods. It's not possible to do unless I cut it down, or 3 lab periods. 4 labs and 3 lab periods, that may be more manageable. And then we have experiment 10 here. Here we have 1 lab over 2 lab periods, so that's a lot better. And then we're starting experiment 8 here, which is a paper lab. Part 2, it depends on how well it goes. You can finish that pretty quickly, or it might take extra time. Experiment 11, this is one lab over 2 lab periods again here. And it's broken up into what we call a known and an unknown. And we'll talk about that more later. The midterms are going to be on exam days here. So our first one is going to be on week 1, 2, 3, week 4. And what material will be covered on that? Well, it looks like it's going to be chapters 1, 2, 3, 4, and 5. It's likely that 5 will not be on this exam. And so it's likely it'll just be chapters 1 through 4 will be on exam 1, maybe part of 5, depending on how far I get. So if I don't hit it on exam 1, I'll get to it on exam 2. Exam 2 looks like we go through chapters 10, but again, probably chapter 10 won't make it there. We'll probably be up through 9. All right, so what I do for the homework is I just collect all the homework on the exam day. So if we have chapters 1 through 4 for exam 1, then I'll collect homework for chapters 1 through 4 on exam 1. And so this one I'm going to collect electronically and just scan it, and upload it on Canvas. It might be a lot of pages to scan. All right, so that's the homework. The homework is on a link here. So let's take a look at the homework. So, we could do that. So I may be modifying this homework. Come in here. All right, these numbers are for the 6th edition, so I need to cross-reference this with the 7th edition to make sure the numbers haven't changed. Some of the homework assignments have a lot of questions. This one, 31. Probably the longest assignment will be chapter 6. Chapter 6, I signed all of the problems, this is going to be a long one. There are a lot of questions there. And there are multiple parts. But they range from, like chapter 1, 0 problems from chapter 1, through 60 plus problems for chapter 6. And some of these take a lot of time, some not as much time. It depends on the calculations. So you can be working on one particular problem, it might take you 20 minutes, 30 minutes. If it starts taking you an hour to do a particular problem, then you might want to reconsider, because an hour might be too much time, to spend on one specific problem. And so you can look at the answer. I think most of these problems I assigned are the blue problems. And the blue problems have the answers in the book itself. Not only the answer, but it has a little worked out, like it's a solutions manual. So it has a built-in solutions manual. So you don't have to purchase a separate solutions manual for this. Mm-hmm.
But how much time do you expect us to spend on the homework every chapter?
Every chapter, hours, time, multiple hours. Depends. It depends. It's always a balancing act, because you have a limited amount of time. So if you're spending, let's say, 1 hour on one specific problem, that's too much wasted time there. You might as well just look at the solutions manual at that point. I know a lot of instructors, they don't look at the solutions manual, but there's a trade-off between time and learning, I think. And at this level, let's say your job is to study all the trees in a forest, and so, okay, you get hired, and then you go out there and you only study one tree, and you're supposed to study all the trees in the forest, and you're spending all your time studying one tree. You're never going to get to the other trees, right? And so you have to balance that. One of the things that, I have a bunch of study tips, and the book does as well. But one of the things I learned when I went to UCLA was normally when I do the homework, I just do the assigned problems. That's it. But when I was at UCLA, I noticed that there was a student that sat next to me, and the student got the high score on the test. And I thought, what did that student do to get the high on the exam? So I started talking to them, and one of the things that they did, what it was? They did every single problem at the end of the chapter. So how can you do I thought that's impossible, because there's not enough time to do every single problem at the end of the chapter. But at UCLA, they allowed, at least when I was there, they allowed the complete solutions manual. When I was at Santa Barbara City College, they only allowed the selected solutions manual. So you only had like the blue problems or the black problems or the red problems. That's it. But they didn't care. You can have the whole solutions manual, because the exams were always harder than the homework. That was so they didn't care if you had the solutions manual or not, because they're going to make the exams more challenging. And so, anyway. Do you know how he did it? Yeah, just read the problem, looked at the answer. Read the problem, looked at the answer, and then picked that up. And then, when you do that, then you see all the different variations you can ask for a particular problem. And that way, when it comes to the exam, which are going to throw in extra twists, you're much more prepared for dealing with extra twists if you already know all the possible other ways that they did it. And so that's how I got the high score on the test. So I started doing that too. And so you could do it as well, except we don't have the complete solutions manual, but you could do the blue problems, if you need more practice. If something's easy, then you don't need more practice. You focus on the stuff that you need more practice with. This is especially important because, there's a lot of competition for grades. Like at UCLA, there's a lot of pre-meds there. And the pre-meds, they need to get the high scores. They need to get the high scores to get into med school. So competitive now to get there. And so these are things you may want to try. But just doing the fine problems alone will take a lot of time. But there's certain things, this is written. So since it's written, at least even if you copy, I can't tell if you copy the solution from the solutions manual or not. But I figure even if you copy the solutions from the solutions manual, that's better than doing nothing, like blank. And so in theory, you should be able to get 100% on the homework. That's possible. In practice, rarely anybody gets 100% because of, I think, time or whatever else comes up. I mean, there's still like maybe 10% of the class gets 100% on the homework, but what happened to the other 90%? Things come up, I think. Yeah.
I think we're trying to say that for the homework, it's not about doing the problems, but understanding the concept. So,
right.
And applying that wherever you like those principles.
Yeah, that's good. It's, like you said, it's about learning how to apply. And so this is why I think it's useful, especially at the introductory level. If you're trying to learn the forest, you don't want to focus on just one tree. If you're trying to learn the forest, you go and look at as many trees and plants and animals as possible, right? And the same thing here. You're trying to learn chemistry, so you want to expose. So there's some instructors that have a very simple way of solving problems. Okay, step 1, do this. Step 2, do that. Step 3, but that's only if you're given a particular problem that will fit those particular steps. And that's okay. Like when you're like in kindergarten, obviously they're not going to throw like calculus at the kindergartners or something like that. And so they try to narrow not expose you to the whole universe of chemistry. But in something like this, so this is a college level chem class, they expect you to be exposed to. They don't want to edit, they don't want to like make this, okay, this is too difficult, so we're not going to tell you this, or this is too complex in thinking. No, they'll probably, this is like the attitude that, like UCLA, they don't care for the test. They don't care if it agrees with the homework. They don't care if you've seen it before or if you've never seen it before, or if it's anything like that presented in lecture. They'll throw in like a challenge problem to see, And that what they want is they don't want anybody to get 100%, otherwise they don't get a curve. And so they'll get a curve. If you got a whole bunch of people stacked at 100%, then that doesn't make it an effective curve because you don't know how to spread out the people at the top. And so they'll make a problem that's very difficult. That's usually what I found. But 90% of the exam is this is based on my experience. Every class I've had there, 90% of the test was like just stuff that was presented in class. It was that 10%, the challenge problem, that spread people out. And so what I realized is it's possible to get an A as long as you understand the material that was presented. So 90% was like the homework, 90% was like the lecture, 90% was, and so if you have that stuff mastered, then you're kind of guaranteed an A. It's just if you want the top score or not. And some people want the top score because, they want to stand out.
Do you grade on the curve?
No, I mean, it's just straight. It is curved in the sense that there's going to be, the percentages might change a little bit. Like I've dropped the A cutoff, 89% or 88%. In that sense, it's curved. But I don't grade in the sense that there are some people that grade like a real curve. Like there should be this many A's and this many F's, and then everything gets in between, regardless of what it is. Not that many people grade like that anymore, though.
For the homeworks, are they all due like at the end of the chapter, or is it like
No, they're due before the exam.
so they're all due before you?
Yeah. The due date is the exam date. If the late homework, it's still accepted, but there's a late penalty for that. I'd rather see you do it, by the final. Late homework's all collected before the final. So you have until the final to do that. I understand people run out of time, but that's why I say make sure you have enough time. Did you have a question? No.
Oh, and that's the answer for UCLA was like 90% was like homework, or based on the homework, and 10% was like that challenge, and they divided.
No, when I say 90%, 90% was based on the class, like the lecture and the homework, that type of stuff. That's what I felt. I felt that if you understood the lecture and the homework and had it mastered, then you could get 90%. But there's always going to be that one problem that's going to, or a couple of problems that'll make you think quite hard about. And so, but exposing yourself to see, the more ways that you see how problems are solved, the more tools you have for solving these problems. And so you build up. My philosophy is this, and I'll get to other questions later. My philosophy is this: I go through the homework early I don't wait until the night before the exam. I used to do that. I used to try to cram everything in the night before the exam, but I go through this early. And so that way I get exposed. Okay, then you start to see, in science, we look for patterns. So you start to see patterns in how problems are solved. And so what I want to do is when I go through these, what I want to do is I want to figure out all the patterns that they use to solve the problems. So I'll go through this, and the more problems you see, the more ways that you see that they solve these. And so, but the problem is the time. And so I just use the solutions guide. I'll just use the solution guide and look at it. And that way I can go through them rapidly. But I don't go through them once because my memory is not so great. So I'll go through it multiple times. And then pretty soon I see these patterns. Now I got to get those patterns to stick here. And not only, okay, there's one thing is, a lot of problems on the test are just like repeating, like regurgitating material. And so it's material that you covered. That's like a problem that you've seen, you've done, or that was done in class, and you just have to repeat it. And that might sound easy, but it's not necessarily easy. It would be like, okay, you watch somebody, let's say you want to learn how to play piano, and you watch somebody play the piano, and you go, okay, that looks easy. I'm just going to go ahead and play the piano. Do you think it's going to happen? I mean, if I have no experience playing the piano, I can watch some YouTube video on playing the piano, and I'll pick it up. Well, it depends. It depends on how hard it is. And so what I do is I'll go through all the problems early, and then the way I study for a test is I'll review the homework. I'll review the homeworks, and then that way I can start to, memorize those patterns. This is the memorization part of that. And that way, if a problem like that came up on the test, let's say a problem that came up on the test was exactly like the homework, I thought that was a gift. It was a gift because I had all the homeworks mastered, and I could do any homework type or any variation of a homework problem. And so those were give me problems. But what I found is the more advanced problems were just like variations of that. And so these are variations that weren't in the homework. And so these variations that weren't in the homework, you can pick up, because what happens is, and this is something that as a student I was interested in. I was interested in this because, that one class I told you about, the student sitting next to me, that student got the high. This is my first quarter at UCLA. I got a D on the test. A D. That was like, oh my God. I'm a chem major. This was a chemistry class. It was a chem major, and I got a D on the test. And I think, I have to do something, because for that class it was one midterm and one final. And so I was spending all my time studying, but it just wasn't working. What I had been doing before, because before I was on the dean's list and this kind of stuff, I didn't have that much trouble with that. But when I got to that class, it was difficult. And so I needed to do some changes. So at that time, I started reading about all these studying tips and whatever else I could find, because I had to make some kind of change, either that or change my major. But and so I was reading about like the neurons and how many connections. Like each neuron has how many connections? Do you know? Like initially there aren't that many branches or connections, but I think it's like 36,000. Is that right? Some of you bio people. I went to this talk at UCLA. It was maybe 4 years ago. They were talking about listening to the brain neurons. They have some like real-time recordings of the brain neurons firing off. They give off electrical signals. And this guy in physics, he was specializing in physics alone. Then he started working in biophysics. And then what he did was he made something to amplify the neurons so you could actually hear them clicking. And so there's a recording in the talk. Talk was a talk at UCLA, but there's some recordings online. You can actually listen to the neurons clicking. But anyway, it's it takes time to develop all the connections. And so, this was clear because after a test at UCLA, there was one problem. It was like 90% of the exam I had no problem. It was down, but that last problem was the kicker, and I was close to solving it. This is on the final exam. The final exams there are 3 hours, and I ran out of time. I thought I was just on the cusp of solving this problem. And then right after the exam, I walked over to Ralph's, and I was in the checkout line at Ralph's, and then it clicked. It's like, I had it. But unfortunately, it was too late. And so then I thought, okay, I got to change that too. And so I started doing it earlier so I could make those neural connections sooner so I could come up with, because all the things are timed, there. It's all times. You start at this time, you end at this time. If you're 1 minute over, you start losing points, on the test. I didn't like timed exams. And so I had to train for speed as well. So anyway, those were some of the things I did. Okay, well, we'll take a break here let's take a break for 15 minutes and then we'll start at 10 after. All right, one of the things I was told as a student was to avoid using the solutions manual. You're not really learning if you use the solutions manual. And so I always had that conception, but I found for myself it was very effective. It was very effective because I put it this way, it's like there's no need to reinvent the wheel. The wheel's there, you use it. And so, these tools are there, you use it. What you want to do is you want to come up with the new inventions. So you want to build up on that to do it. And that's what the challenge problem was, the 10%. And so if you have these down, then getting the challenge problem is going to be a lot easier. Another thing that I was told was to read the chapter, before lecture. But I never had time to read the chapter. I always read the chapter after lecture. So this is the second component that I was talking about. It's not just the homework that the exams are based on. It's 90% homework and lecture material. Sometimes the lecturer talked about nothing in the book. They were talking about something else. And then that stuff pops up on the exam. And then, you might complain, hey, that wasn't in the book. That's not fair. But they don't care. Whether it's fair or not, they want to get that spread. They want to see what the distribution is, And so, what I did was I never read the book before. I always read the book after. That way, I knew what to focus on. Especially some of these classes had a 1,600-page book in 10 weeks. How are you going to read 1,600 pages? This is an engineering class they took there. In 10 weeks, it's impossible, because it's so slow, the reading is, like 1 hour later, I'm only 10 pages in, it's like, and so I always did that. And so what I do is, if there's stuff I didn't understand in the lecture, I would look for it in the book, and then I'd look for it in external sources so that I understood it before the test. That way, if it occurred in that 90%, I already had it mastered. And so that's something else that I found quite effective. And so doing those two things really helped my grades at UCLA. But I pulled out of that nosedive, fortunately, and was able to recover in that class. I think I didn't get that great of a grade, but that's okay. All right. So today we have these 3 hours. So chapter 1 is pretty short, but it has some important topics. So I was debating what to do for this particular semester. Was I going to go PowerPoint or just handwritten notes? And I took a survey from different people, and a lot of people seem to prefer PowerPoint instead. So let's try PowerPoints initially. See how that goes.
I have a question, taking it back to the syllabus really quick. Do you allow makeup labs if you necessary?
Makeup labs, because we have it depends. If it's like a multi-day lab, then those are a lot easier to make up. Or let's say you're absent in the morning, but there's an afternoon lab meeting, my afternoon lab, and you can make it to the afternoon lab, then those are okay to make up. But makeup labs are tricky because the equipment that they set up is only out for that particular lab, and not all the instructors are doing the same lab. So most of the time, it's not possible to do a makeup lab. Sometimes you can do a makeup lab in a different section. So let's say there's an instructor teaching that particular lab, the lab setup, and then you can ask if there's room. In general, they'll let you make it up there, but makeup labs are a lot more difficult. Some easy, some might not be so easy. So I'm going to go with PowerPoints. We'll see how that goes. These are the PowerPoints that come with the book. And it's like this. Do you think on the test, every sentence in the book is going to be of equal importance? You know, when you study it, do you have to know every single thing in the book? No. And so what we want, this is why I never read the book before class, because I wanted to know what was important. Was this important to the instructor or not important to the instructor? You know, the chances are we going to have this on the test or not have this on the test? If chances are we are not going to have it, I'm not going to spend a terrible amount of time studying it. I just focus on the stuff that was covered in class. So I'm going to download this, open it up in PowerPoint here. Okay, I'm going to probably edit these slides here. Let me get rid of that. So I'm not going to do a slideshow because I can't. Like that. But here, chapter 1 deals with introduction to chemistry, introduction to active learning. And so the active learning is this thing that Krakowicki has, and he tries to incorporate this into the book, and so he talks about this. I'm not going to spend very much time talking about that. So, introduction to chemistry, Lavoisier and the beginning of experimental chemistry. So there's some history here. You aren't going to have to know the dates, but you'll have to know some important scientists. Lavoisier is one of them we can talk about. Introduction to chemistry, science, and the scientific method. This is, I find, very important, the scientific method especially. And the situation is, it's important that another reason you want to go to lecture is so you can see, sometimes they emphasize different things, like different instructors will do things, not only emphasize different things, but will do things differently than the way it's presented in the book. And in fact, I have, the scientific method that I have is a little bit different as far as how it's organized than the book. Essential components are there, it's just organized differently. Introduction to chemistry, the chemistry of today. So yeah, 1.1 through 1.4 chemistry, and then he goes into talking about this active learning stuff, how to learn chemistry. How to learn chemistry, he gives tips as well. You know, you try doing this, try doing that. You know, I've when I was a student, I've had lots. One instructor said to be successful in their class, you have to read the chapter 5 times minimum. You know, which I never did. Certain sections of the chapter, yes, I'd read like over and over because it just didn't click. Eventually, it clicked, but not the whole book. But there's some other tips. Active learning, your textbook of choice. So let's look at this definition of chemistry. Science that studies how molecules behave. You know, is the universe only made up of molecules? Do you know what molecules are? Like H2O is an example of a molecule. And a molecule is,
Oh, I thought you were asking if you knew what it was.
oh, okay, yeah, go ahead. You have the
It's
definition?
like, okay, so this, you know, you have oxygen and hydrogen,
Mm-hmm.
how they like form together.
Yeah,
That's a molecule.
that's a molecule, exactly. Like oxygen and hydrogen kind of combine together to form a molecule. And a molecule is a discrete particle. Discrete particle. And so, like molecules of water exist. So if you take some water and you want the smallest piece, what is the smallest piece of water you can have? And it wouldn't be a drop. A drop would be large. In fact, a drop consists of so many molecules you couldn't even count them. You know. But if you keep taking smaller and smaller pieces of water, what's the smallest piece of water you can have? Well, the smallest piece of water you can have is a discrete unit, and it contains two what we call atoms, hydrogen atoms, bonded to an oxygen atom, and we call it H2O, and that would be a particle of water. But, you know, sometimes people say, okay, I want a molecule of table salt. And the problem is table salt doesn't form that type of structure. So we wouldn't say, that would be wrong to say, okay, table salt consists of molecules. Table salt, do you know what table salt's made of?
It's like sodium.
Sodium chloride. Sodium chloride is what table salt's made of. And we call water H2O because it contains two atoms of hydrogen and one atom of oxygen bonded together to form what we call a discrete molecule. But is there a molecule of sodium chloride which takes one atom of sodium and one atom of chlorine, which we call chloride in that case, and forms a molecule of sodium chloride? And it turns out, no, sodium chloride does not form discrete molecules. And so not everything forms discrete molecules. Is there a molecule of wood? You know, like one little discrete, if I took the wood and broke it into smaller and smaller chips, would I eventually get to a molecule of wood? No, wood isn't like that. Wood forms like what we call a polymeric structure. It goes long. It's the same thing as plastic. You know, plastic forms these long, you can consider it a gigantic molecule perhaps, but there's no really distinct beginning and end. It could just go longer and longer and longer or shorter and shorter. You know, it depends on how long it is.
Can you expand on what you mean by discrete molecule?
A discrete particle.
Okay.
A discrete particle. Discrete particle would be it's a standalone unit. Whereas like this plastic here consists of a whole bunch of molecules. They all look the same, but their lengths are different. You know, and we call those polymer. They're chains. These chains, and there's no distinct. Like the chain is it 30? We'll call atoms long, or 60, or 100, or 1,000. You know, well, it could be any of those. You know, it's not discrete. Whereas water is, could you throw in 3 hydrogens and 1 oxygen in water? No, you can't. It comes just in a unit of H2 and an O. And so, so it's like a crystal of sodium chloride. A crystal of table salt you can break into smaller and smaller pieces, and but each of those would be what we call that. So some certain things occur as molecules, other things occur as lattices. You know, these lattices are these chains or these more complex structures, and these more complex structures can be big. Like, for example, a diamond. Is there one size diamond crystal? No, they're different size diamonds, bigger ones, smaller ones, and they're all diamond, right? And so it's not really discrete. There's not, it's not built up. Well, we can have the same thing with water, but water would just consist of it. And so they call molecules the smallest unit particle of a pure substance that can exist independently. This is the key word here, independently, that is discrete and possesses the identity of the substance. So not everything occurs as molecules, so I don't particularly like this definition that much. Chemists ponder on things that make up the universe, such as molecules, but the universe isn't made up entirely of molecules. In fact, the sun, it's so hot on the sun that any molecules there are completely obliterated. They're torn apart. Like if you try to have water there, it's so hot there. Hot is what we call like kinetic energy. There's so much energy there that you get these collisions, these massive collisions that break off the hydrogens from the oxygens, and we end up with parts of these things. And so I like chemists study matter. It's the science that studies matter and how matter behaves. And not only that, I told you what matter is. Matter is, or you guys also told me what matter. It's anything that occupies space and has mass. But chemists also study vacuums. They study energies because vacuum is very interesting. Vacuum is the absence of matter. The absence of matter is very critical for things like you have to keep very clean. If you don't want anything in there, what's the best? Well, vacuum. There's nothing in there. So people have been trying to get a vacuum on Earth. Problem is, it's too difficult to get a vacuum. You try to suck all the air out of here. It's very difficult to get and air consists of molecules. Every molecule of nitrogen and oxygen, there is nitrogen and oxygen out of this completely to create something called a perfect vacuum. Because there's going to be just a little bit of residual air in there, a little bit of contamination. And so they get more and more powerful pumps, but they still haven't achieved a perfect vacuum on Earth. So why you want a perfect vacuum? Because, when you're manufacturing things like silicon chips, you don't want any contaminants to get on there and get incorporated into those chips.
Even oxygen can contaminate those chips.
Well, there's a potential. It's not just oxygen. Oxygen, probably not. It depends on certain things. Certain things you want certain molecules out of there. Other molecules are okay. Maybe nitrogen. So there are different things we have. We have vacuum, so we can try. There's a funny story. They're trying to synthesize chips, and so creating a perfect vacuum on Earth is so hard. But getting a close to perfect vacuum in space is a lot easier, right? And so they took the space shuttle out there, and they had this little arm that would transport their scientific apparatus out of the space shuttle. So they have this thing, and they're going to try to grow some semiconductor crystals. And they thought, okay, these are going to be the purest semiconductor crystals ever grown because the vacuum out there, there's practically nothing there. It's the emptiness of space. And so they brought those, and I don't have the exact details, but they brought them back, and they turned out to be highly contaminated. I mean, worse than the ones they grow on Earth, right? And do you know why?
Because the reaction.
The reaction's fine. It was because of contamination. Do you know where the contamination was coming from? Yeah, the space shuttle itself. The space shuttle itself was degassing all the contaminants off the surface tiles and whatever else, and heavily contaminated their crystals. That's how the story goes.
A vacuum is the absence of matter. A vacuum is the absence of matter.
Yes, but that one was not close to a perfect vacuum because there's too much stuff coming off the space shuttle, and ended up contaminating that. But yeah, this type of stuff. There's another story. I went to a talk with IBM, and they were talking about they have clean rooms. Like if a piece of dust gets in there, that piece of dust ruins. I mean, piece of dust is a lot larger than chips nowadays, and completely ruin it. And so they have a certain discard rate, so they get cleaner and cleaner rooms. It's not a vacuum because you can't work in a vacuum. But nitrogen and oxygen are okay because they aren't going to ruin it, but dust will. And so they're talking about, okay, they got this level 5 clean room, and they got this higher level, but they still have the same percentage of defective chips. I was saying, why are they getting the same percentage of defective chips when they're getting a cleaner and cleaner and cleaner room? And so this IBM scientist was talking about the utility of having a broad perspective. A lot of people say, "Oh, I'm never going to use chemistry. There's no reason to take it." But this person was arguing the opposite. You should try to expose yourself to as many things as possible. It's like this homework. You try to expose yourself to as many different ways of solving the problem as possible. And so, what this IBM fellow said was he was sitting in, I think it was like an astrophysics seminar where they were talking about cosmic radiation, and then it clicked. It must be because of cosmic radiation. That's what it was, because the room was so clean. They weren't expecting it. And so what they did next was they shielded the facility for cosmic radiation, and then their defect went way down. And so this was just an example of exposing yourself to a broad
What is cosmic radiation?
cosmic. We're constantly bombarded by these high energy, either photons or particles. They call cosmic radiation, and so we're constantly bombarded by UV radiation. That comes from the sun, and we're adapted for that. When I was taking biochemistry, which is many decades ago, the biochemist, I still remember this number. The biochemist told us that the DNA is these, I think everybody knows DNA, but these long chain molecules, they're discrete, and they contain atoms. There are a lot of carbon-carbon bonds there, and these carbon-carbon bonds are cleaved by UV radiation, light. And so they mentioned that the DNA gets cleaved 200 times. Well, if your DNA gets cleaved 200 times a day, that's going to cause mutations because, things are, information is lost, basically. It's not transferred correctly. But fortunately, your skin has repair enzymes to fix the damage. And so you don't end up with cancer or a lessened risk of cancer.
Sunburn would be like more than 200 creams a day?
So now, back in those days, you didn't have to wear sunscreen all the time, but because of the ozone, there's some less ozone. We have less protection from UV. So DNA is probably cleaved a lot more than 200. Does anybody know the number? No? Yeah. Well, that's just from the sun. And then you're exposed to cosmic radiation also. And the cosmic radiation can also break bones. It has enough energy. We worry about, this is why we study. We study energy, even though it's not considered matter. We study energy because energy can interact with matter and do different things. It could cause things to vibrate. That's what we call infrared energy. Or it could cause bonds to break. Or it could cause the atoms themselves that make up the matter to break off pieces of it. And one of the pieces that gets broken off are called electrons, and that's called ionizing radiation. So we get exposed to ionizing radiation, which all cosmic radiation is, and so that can knock electrons off and cause the process called ionization, which we'll talk about later. People who travel in airplanes are exposed to, I guess, a lot more. In fact, there was some talk about radiation exposure when Fukushima, Fukushima, the nuclear power plant in Japan, they had that disaster, and they were talking about radiation exposure, and they were comparing it to cosmic radiation. Oh yeah, this is going to be less than cosmic radiation of taking an airplane, so the amount of exposure that you leaked. And they're talking about, the government there wants to, they have a bunch of radioactive water that they want to get rid of. And have you heard of this? They're running out of storage, and what their recommendation is, and it was already approved. The recommendation is to dump it in the ocean, and so they're going to dump this in the ocean because it's hard to remove certain isotopes from the water. And they're thinking, once it's diluted and the amount of radiation you're going to get compared to this or that, but it's a little bit different because cosmic radiation, it's there and then it's gone. But certain radioactive isotopes, like radioactive iodine, I think they're going to clean out the iodine out of there, or radioactive strontium. Iodine gets concentrated in your thyroid. So this is why, when there's a nuclear disaster, like, for example, in Chernobyl, some of the countries around there gave their citizens iodine tablets They gave their citizens iodine tablets to saturate their thyroid so that when they were exposed to the radioactive iodine, there was less of a chance of it getting incorporated into the thyroid. And so those countries had very low rates of thyroid cancer, whereas the countries that didn't give their citizens any iodine supplements had a much higher rate of thyroid cancer. And during Fukushima, they were talking about, their diet's rich in seafood and there's lots of iodine from seaweed and this kind of stuff. So they didn't give. They were saying, there are negative effects of iodine, potential side effects. But they have a fairly high thyroid cancer rate with that. But we get exposed, and then there were we get exposed to radiation all the time, basically. And so how you treat it, some people will think nothing of it. Other people think it's more serious. The cosmic radiation. If you really wanted to protect yourself from cosmic radiation, maybe you'd have to wear some lead, like a lead hat or something, lead shoulder pads or something like that. Or the cosmic radiation might be coming from front, so you'd have to live in a bubble, basically. And so this is, these types of things have to be balanced, I guess. But I don't think that when I was in elementary school, we were drilled this: the solution to pollution is dilution. But then you hear stories like the brown pelicans. You know about the brown pelicans? The brown pelican population on the Channel Islands dropped precipitously. It was because of they used to dump a whole bunch of DDT in the Santa Barbara Channel. And they thought, okay, the DDT, we'll dump it there. The solution to pollution is dilution, and it'll just dilute. But it turns out it weakened the egg of the brown pelican. The population made a comeback, but it's not always the solution to pollution. But this is another, chemistry. Chemistry they call the central science, and one of the reasons they call it the central science is because the universe is made up of matter. And what do chemists study? Chemists study matter. Its properties, both chemical and physical, its structure and its composition. And so that's the definition I like. I don't particularly like this, so I wouldn't spend much time memorizing this or doing anything with this here. Antoine Lavoisier, the father of modern chemistry. So why do we need published in 1789 this chemistry paper, book, but it marks the beginning of modern chemistry. So what happened before Lavoisier? And so, and in other words, the reason I think Lavoisier is important is because it marks the beginning of the scientific method. And so Lavoisier here is going to be tied in with the scientific method, experimental chemistry, etc. And so let's talk about this, but let me give you a little preview here. What do scientists do? If you think, what do scientists, okay, so chemists study matter. And then how do they study matter? Like, if you think of Isaac Newton, this is a classic example. What did Isaac Newton do? Yeah, but what did he study? What did he observe?
An apple falling?
Apple falling from the trees, how the story goes, right? Isaac Newton observed an apple falling from a tree. Well, that's pretty much what all scientists do. What scientists do is, and this is what, let's see if this is working. Oh, shoot, it's not working. Let me do something really quick here. Okay, now it's working. What scientists do is they observe nature. That's what Isaac Newton did. He observed nature. If you're out there studying forests, what are you doing? You're observing the forest, right? That's what scientists do. Observe nature. And based on this, you can see how nature behaves, the behavior of nature. That's what we call properties in chemistry. So we're looking at observing properties of matter. And science is science is just a description of nature, describes nature. So if you're a chemist, how do you want to describe it? You want to describe it as detailed as possible. Like water, yes, water is what we call a clear, colorless liquid, but we want more detail. You know, what is it made out of? What is its composition? Well, water is actually comprised of the elements, and it turns out that there are a finite number of elements there, about 120 elements or so. You know, not all of them are found naturally on Earth. But not only that, the universe is made up of these elements as well. And so this is what makes up matter, the elements there. And you can get smaller pieces than the elements, but for chemists, this is where we stop. And so we want to know the composition, we want to know the structure. Water forms discrete molecules. Table salt does not. And so we'll talk about table salt later. But you aren't going to find molecules of table salt like you would find molecules of water. What we find is a lattice. So we describe nature, and the properties are going to be different because of the structure and the composition. Mm-hmm.
The PowerPoint is uploaded on the campus?
Yes. I uploaded it last night because I wasn't going to use the PowerPoints, and then I decided at the last minute after talking to somebody to use them. Yes. Yeah. I'll post this on Canvas as well, the edits. So the science, we describe nature, so we want to get to the nitty gritty of this, or whatever you want to call it. Basically, we want to know the composition. I want to blow this up bigger because this is hard to write. And we want to correlate it with the structure and the properties. So if you want to know, let's say you want to know how a machine works. Well, you got to know what the machine is made of and the structure and the resultant properties. And so this is chemistry here. It's the composition, structure, and properties of matter. And matter is what makes up the universe. Prior to Lavoisier, there was some like magic involved. You know, that is, this is very simple. What do scientists do? Scientists observe nature, and what does science do? Science describes nature. But prior to this, we had something called alchemy. It sounds like chemistry, but it's not exactly chemistry. Alchemy is a mix. You know, there was science for sure. You know, there's observing and describing, but some people took it a bit further because there was some magic involved as well. Science and magic. Well, we call it magic. Well, what do I mean by magic? Well, what I mean by magic is like alchemists. You know what alchemists were really interested in finding? They're really interested in finding the elixir of life. Have you heard of the elixir of life? Uh-huh. Yeah. Yeah. Actually, let's see what we have. Let's try to get some visuals in here too. Alchemy is the medieval forerunner of chemistry, but they're interested in the elixir. You know what the elixir would do if you drank the elixir? Hmm? Yeah, yeah. Well, the elixir of life was it would make you immortal, basically. And so that's an extra step because all science does is it just describes nature. That's all it does. You observe it, you see, apple falls. What do you want to describe? You want to describe how long did it take? How fast was it going? Was it accelerating? Did its speed change? What would its ultimate speed be if you dropped it from 20 feet or 3,000 feet? That kind of stuff. That's just a description of nature. But alchemists would say, okay, when the apple hits the ground, then it would be transformed into a pear or something like that. That would be more alchemy. That would be the magic end of things. And so there's the separation. So, for example, do you want to dedicate your life looking for the elixir of life? What types of observations would lead you to believe that you can find or make the elixir of life? Uh-huh.
Did they ever find the elixir of life?
If somebody found it, they're not telling. But it would be great. I mean, that would be great. Uh-huh. Maybe.
I thought they were like talking about like water.
Yeah, water is the elixir of life. In biochemistry, when you take that, chapter 1 is all water. Because if there wasn't water, then there would be no life. Uh-huh.
I believe like maybe they could like observe animals that would act immortal or have behaviors that could be considered immortal. Like jellyfish can technically be immortal, I believe.
Oh yeah, that's true.
So maybe they would do that. Or
Yeah.
try to see people who live a long life to see like what they could perhaps recreate to get more for life.
Mm-hmm. Yeah, there are some things that could be considered. Like what else? There was one other thing. There's one other thing I just read recently that essentially has that. But for humans, what would you think? I mean, okay, you could start studying jellyfish and then you look for longevity. In fact, there's a very interesting book that I've been reading. I haven't quite finished it yet, but this book is proposing that we could potentially be immortal, but it's not because of some magical elixir. It's because of certain things. What's the name? I set it down, and my memory is really bad. I have to. I need a lot of repetition, but I recommend this book because it is science. This is trying to find the elixir, quote, elixir of life. Sinclair, this guy's a professor at Harvard. He wrote this book. Let me give you the name of the book. What is his book? I think his book is. I don't pay that much attention to the title. I should pay more attention to the title. More. But he says aging is loss of information, basically. And so, your DNA is supposed to have these certain type of structure. And as you get older, a little bit of that is lost. And as that happens, you start to lose that information. As you start to lose that information, then you start to age. And so there are certain things that you can do to retain that information. And so what he's proposing, let's say if you do this and you get 5 years of additional lifespan, then you think, great, okay, that's 5 years, but he says you can do it again, and then do it again, and then do it again. And so if you continue to do these things, then there's a potential for immortality in that sense, that kind of. And so the book is very interesting. And some of the stuff is not difficult, but it's weird because there's some supplements that he recommends, like NMN and some of these other supplements. And it's weird because, I was able to buy those on Amazon, and then all of a sudden they're gone. It was the same thing as COVID. When COVID hit, some people were recommending. There's a professor of medicine over at UC Riverside. He was recommending a certain type of supplement. Um, and not just for COVID, but also for the flu, and other things. And so I ordered that supplement on Amazon as well. But as soon as it was associated with COVID, like a potential, something that potentially helps, alleviate whatever symptoms or something, then Amazon killed it, and you can no longer buy it on Amazon. The same thing with these supplements, NMN. So I started taking NMN based on his research here, and he has good observations for this. Good observations that support it. Why do you believe in the elixir of life? Can you convince somebody? I want to convince you to dedicate your life to finding the elixir of life for me. Can I convince you? You know, you better have some good supporting evidence. Some what is good supporting evidence? Some good observations that make sense. To do something. And that's what science is. It's just observing nature and then seeing how it behaves. Uh-huh.
What about Sinclair? You mentioned that you extend your life by 5 years.
Yeah.
It's like you're doing that even forever. Question was what age would you, if you just keep going old by just learning, what age would you remain?
Well, yeah, the aging would be slowed down. It would be like he says, and he has a bunch of videos out, YouTube videos, and other talks. And so those are a good place to start if you're interested in this. But he says, what good is it if you're going to be suffering from a lot of disease? And so he says aging is a disease that's treatable. And a lot of these diseases that are associated with old age are according to him, things that should be treatable, that you should be able to avoid. And so at what age you would just slow down the clock considerably so you would be younger. But of course you'd have to age because there's certain things you cannot stop. But it's very interesting. You should read the book and then see. But this is science. This is I guess the elixir of life from post Lavoisier versus a pre Lavoisier would be some magical potion that you got to find, and so you have to get in connection with the right magician or the right whatever to get it. Not only was there the elixir of life, but there was the philosopher's stone. Have you heard of the philosopher's stone? Philosopher's stone would take a base metal and convert it into gold. And so the philosopher's stone might be based more on observation because maybe these alchemists saw, there's some chemistry involved. They have these, and they saw these physical transformations that, and it wouldn't be a physical transformation, it'd be a chemical transformation. So they saw these chemical transformations. And what was the difference between a physical transformation and chemical transformation?
The chemicals cannot go back to the original state.
Yeah, well, we'll learn later it could, but it's quite different. The chemical state in a chemical transformation has changed considerably. It's no longer, for example, water. It's something else. And so those were known. So philosopher's stone, maybe there are more observations for, but still. And so here, philosopher's stone, and then air, sulfur, silver, potassium. So there's these, and they're looking at chemical reactions. And so,
Is that like, I guess, whatever in the periodic table?
right. Right. And so it's a mix. It's a mix of science, observations, and magic, because they're predicting, that something like this. Whereas in science, we wouldn't make that kind of prediction. Like Sinclair can make that prediction because he has some hard observations that back it up. He's saying, like, one of the weird things is he's talking about reversing aging. And so he was talking about, and this isn't part of, because everything has to be randomized controlled trials, but he's talking about like some like menopausal women becoming fertile again, this kind of stuff. And so there's actually some things that, and as well as reversing the effects there. And so but it wouldn't like make you younger in that sense. But there are certain things that will make you younger. But but those are very specific. So that's an example of this. And so all Lavoisier did was he said, we're not going to make this magic stuff. What we're going to do is we're just going to take observations. And that's what we do in science. We just take observations. And this is the scientific method. The scientific method begins with observation. And what do scientists do? They observe nature. Why do they observe nature? Because they want to see how it behaves, its properties. And to understand the behavior, they need to understand what? If you want to know how, let's say, a car works, then you got to get under the hood and take a look at what's going on right there. And so it's the same thing here. We want to look at the composition and its structure. And we do that. Right, so that's basically it. You don't need to know his publication, the date, or anything, but you need to know he conducted experiments. What are experiments? Experiments are just careful observations. You know, the more detailed observations you take, the better the experiment. The more what we call quantitative the experiment is. Like Newton. Newton just didn't watch the apple drop. You know, Newton measured the distance, timed it, a whole bunch of stuff. Right? Which one? That's supposed to say properties. Okay, then this was kind of a revolution because Lavoisier wasn't predicting the elixir of life. He wasn't predicting the philosophy. He was just watching nature. And so, just like Newton, Lavoisier watched. For example, watched mercury and phosphorus burn in air. Before this, there's something called this phlogiston theory. You know what a theory is? We'll talk about that later. But the phlogiston theory proposed that all matter that has the ability to burn contains phlogiston. In the process of burning wood, this phlogiston is lost and ash remains. And so when you burn something, there's a chemical. That's a chemical change because it's no longer paper or wood. But what happened to it? You know, well, it was converted into something else. And what was it converted into? It was converted into phlogiston, this invisible, mysterious substance. And so this was kind of magical because, well, you know, in a sense. But theory, there's nothing wrong with this. A theory is fine. A theory is part of scientific method. And so you could propose any theory you want. You know, there are a number of, well, we shouldn't call it a theory. You know, in science, we have a distinction between a hypothesis and a theory. You know what the difference between a hypothesis and a theory is?
A hypothesis is a prediction, and a theory is the highest level of knowledge, or what we believe to be the closest to the truth.
Yeah. That's essentially it. A hypothesis is a prediction, and the theory is the highest level. But the highest level of knowledge, which we believe to be the truth, is it has to have widespread acceptance. And so if you have two competing theories, well, we shouldn't call it two competing theories. We should call it two competing hypotheses, because once it hits the theory level, then it should be accepted by both competing parties. In other words, if you have two competing theories, then one side has to convince the other side. Once one side convinces the other side, then we have a theory. And so we should call it a hypothesis, because a hypothesis is like a theory in development. You could have two competing hypotheses. So we should call this two competing hypotheses. One hypothesis is that the phlogiston stuff is lost. The other hypothesis is, I don't know, we'll look at his hypothesis next, but it's like this. There are two competing hypotheses. You know, in science, it should be, you can propose any hypothesis you want. The thing is, you have to convince the other people. How do you convince the other people? You convince the other people by Evidence by observations. I got these observations. That's evidence. For example, there are two competing hypotheses about coronavirus, COVID, right? One hypothesis is that it came from pangolins and bats. The other competing hypothesis is it came from the lab. It was an accident, or maybe whatever. An accident's another hypothesis. It just came from a lab leak. And so how do you convince people? If you have two competing hypotheses, then one side should try to convince the other side that their hypothesis is correct. But in science, it doesn't, there's a lot of non-scientific stuff going on because one side wants to prevent the other side's information from getting out. Is that a scientific argument for adopting their hypothesis? So they want to discredit. Well, how did they discredit the other hypothesis? They discredit by saying it's worthless, but that's not really discrediting it because we want observations to discredit it. So if you want to discredit, let's say, the lab leak, or you want to discredit the animal, then we need observations, and that's the modern scientific method. You could propose any ridiculous hypothesis you want, but it's fine. Every hypothesis should be valid until, well, not valid, but every hypothesis should be heard until there's evidence to prove it wrong. Right. And so there are people who hypothesize that their atoms don't exist. That's fine. But we need to see the observations that support that hypothesis. And so there's been a lot of censorship in science. Censorship is not good for science. Censorship is bad for science. Science is self-policing. There's no police. There's no one person or one group who defines science. My definition of science is what is correct, and everybody else's should believe and trust my definition. That's not how science works. How science works is there's always healthy debate. And sometimes this healthy debate gets kind of intense, so that sometimes when you go to these scientific meetings, it looks like they're actually kind of fighting each other, but they're not really fighting each other. They're just trying to iron out the truth, And so sometimes ironing out the truth requires this open discussion of ideas, whether you think their ideas are worthless or not. If their ideas are worthless, then it should be easy to disprove, shouldn't it? And there should be no need for censorship. And so that's one of the things that really bothered me recently with recent science that's been going on, is because of this censorship. There should be no censorship in science. Or maybe not acceptance. You just want to be skeptical. Scientists are full of skeptics, so they don't. And you'll find this at scientific conferences. You'll go, boy, because the people in the audience will be picking at you, and then they're thinking, oh, they're trying to tear me apart. They're trying to all my ideas and stuff. No, they're just trying to, they're skeptical, and they just want to be convinced. You have to convince them. So it's like, okay, I'm here. This is my elixir of life. I'm going to sell it to you today for $100. And then you'll get that person in the audience. Well, this, and they don't believe them. They need to see some evidence, some support to believe that. Versus other people that go, okay, that person's trustworthy. I trust that person. They're saying it's the elixir of life. I believe them. That's not science. Yeah. And so this is the beginnings of science. And so this is why Lavoisier is important, because Lavoisier is entering experimental evidence. What's the observations? So the Sinclair guy at Harvard, there are lots of skeptics. This guy was attacked, brutally attacked. This guy's out. This guy's a nutcase, right? But if somebody says this is a nutcase, what do you say? Oh, I trust you because you're a well-respected scientist? No, they're a nutcase because of this. You don't want to hear they're a nutcase because I said so, I don't, anyway. So you read the Sinclair stuff and you go, wow, he does have a lot of supporting evidence. Maybe there is truth in this, and maybe we're on the cusp of having at least maybe not immortality, but very extended. He's talking about significantly extending lifespan. So much so that I went on Amazon and bought NMN, and now you can't even buy it anymore on Amazon because I don't know. The Amazon, there's somebody there who knows the science, and they don't want any bad science to go out. People should be able to make up their own mind, I think. Not have some company or somebody tell you what to think.
Is it mercury that burns white? Or is that something else?
Mercury, it will burn and form a white powder.
Yeah, is that why it gets
Phosphorus also burns white too. Both of these are very unusual because both of these, the ash, both of them have white ash, and the ash actually weighs more than what you start off. When you burn wood, the ash is less. So the phlogiston goes away. But what Lavoisier said is this phlogiston, I have experimental evidence that there's no such thing as phlogiston because what's happening here is when he burnt the mercury and the phosphorus, something came on to it. Nothing left. And so it was for Lavoisier, it was easy to disprove this theory as it was proposed. So if somebody was saying, okay, when you burn wood, the phlogiston disappears, and then Lavoisier's in the audience, Lavoisier is saying, well, what about this? This, if you can't explain this, then this disproves your theory, your hypothesis.
Is science objective or objective?
Science is objective, but humans are humans, so there's a lot of subjective too. And then, eventually things police themselves. So eventually, like scientific fraud eventually will catch up. It might take some time. This is why there are some professors, like at UCSB, there are two types of professors, because I was a teaching assistant at UCSB. So there's some professors, they didn't care about the cheaters. They thought, oh, they can cheat because it's going to catch up. Because once you get to, let's say, upper division, you have a big class like Chem 1A. There are 300 students there. But once you get into these smaller and smaller classes, it's very easy to see, and they're weeded out quite quickly. People who just cheated to get there because they're too weak. They can't keep up with the class. It's too hard for them. And so they're that mind that eventually they'll catch up and they're going to change their major, so they don't care, basically. And then you have the other guys who are just fanatical about it. There's one, it was so funny. There's an ID check for the exams. So they check their ID. And but this professor knew who that student was because they had talked to them before. And then they saw that person, even though they looked similar, they weren't the same person. And then the professor confronted the student. And then the student took off running. And then the professor took off running after that student. And then there's other TAs that took off running. And so all of a sudden it was like this big chase in the lecture hall. Anyway, they caught the person. And that guy was, if there was going to be a policeman of science, that guy was it. Anyway, so getting back to this, what do you need to know about Lavoisier? Lavoisier just did observation. He didn't. There wasn't the subjective part. It was just observations. What happened? When phosphorus burns. Phosphorus burns. What happened here is different than wood. If you put a piece of wood in here, this balloon would grow bigger. And the balloon grows bigger because that would be the phlogiston. But here, when phosphorus burned, the balloon shrank. And that means the air that was trapped in here is less. There's less air in here. And not only that, the ash that remains weighs more. And so this is just an observation. The observation was this, before and after. And so the first step in the scientific method is taking observation and seeing if there's a pattern. And you got to see if this pattern is reproducible. So it doesn't matter. You take a little bit of phosphorus, a lot of phosphorus, and burn it under different conditions, you always see the same thing. Yes. You always see the same thing, so we see a pattern there. And then once we get a pattern, then we see if that pattern is very reproducible, then sometimes we call it the law, the law of burning. But the law really doesn't tell us what's going on. And so the nice thing about phlogiston was that it was telling you what's going on. We're losing some stuff in this case, but what's going on here? And so there has to be some kind of hypothesis. And there was a law that came out from this. This pattern is very reproducible. And one thing is, can you weigh air? Have you ever, do you have one of those canned air tanks that dust things? Do you know when it's full and when it's empty, does it weigh different amounts or does it weigh the same? And the same thing goes if you have an air tank or whatever. You can weigh the air. Air is matter, it has mass. You can weigh that mass, although it's not so easy to weigh. But it turns out that they did this and they did careful measurements, and the weight before and the weight after were the same. And each time they did this experiment, they always got that the weight before and the weight after was the same. And that was a reproducible pattern, and that could be expressed in mathematical terms. And you know what we call that? We call that the law of conservation of mass. In the law of conservation of mass, they took it another step, and they called that the law of conservation of matter. That is, matter is neither created nor destroyed. In phlogiston, the matter was kind of destroyed and converted in phlogiston. But matter is neither created nor destroyed, it's just rearranged. And so the hypothesis here is that, because obviously this is a chemical change, and something happened, it's no longer the same as it was before. And so the matter was rearranged in the chemical change. And so that was the hypothesis. And that hypothesis was backed up by the law of conservation of mass. That is, it was backed up by these repeated observations. And the same thing happens with mercury. When you burn mercury here, the mass before and the mass after were the same, even though there was definitely a chemical change, because actually the mercury doesn't burn white, the phosphorus does. And the mercury burns this red stuff. I have some videos of this I was looking for from the book website. But again, the hypothesis here, and we call it hypothesis because you have to convince everybody. Once you convince most everybody, obviously there are going to be permanent skeptics that won't believe anything. But once you convince the majority of people, then we might be able to call it theory. It has to rise to a little higher level to be called a theory. And so this is anyway, this is the start of the scientific method. And so you don't have to really know too much of the details, but he just took very detailed measurements of what's going on. And so this is the scientific method as proposed by our book. But this scientific method, I'm going to modify a little bit because it's all kind of grouped together. And the scientific method doesn't always have to follow this. Oops, let me give you back the slide here. We always start off with observation here. And this is typically what people do in the laboratory. You observe. Some people say, well, you start off with a hypothesis in science, like in life science. And I can understand why they would say you start off with a hypothesis. But how can you come up with any meaningful hypothesis without knowing something about nature? So can you come up with some hypothesis right now? Some scientific hypothesis? No, it's too hard. And so what we do first is we try to learn something about the field. And let's see if my pen is working. It's not working. Yeah.
It says the device is disconnected.
Disconnected? Yeah. Thanks. Well, haven't.
It's connected now.
Oh, is it connected
Yeah,
now?
you want to try to see if it'll.
Oh, yeah. Thanks. Not disconnected. Struggle with connection here. All right, so the scientific method, the steps are a little different than what they have. I have observation. And so first we observe the initial reaction. And then we want to take detailed observations. We want to be as quantitative as possible. There are different levels of detail. One level is quantitative, where you're taking precise measurements, like Newton. Newton probably measured the distance and whatever else, time, versus qualitative. Qualitative would just be watching the apple fall from the tree without taking any measurement. It just dropped quickly, you could say. Quickly would be versus a time, you know. It was fast when it hit the ground versus a speed when it hit the ground. You know, that's the difference between qualitative and quantitative. In science, we'd like to be as quantitative as possible, but sometimes it's not always possible. And then we look for patterns. If these patterns are reproducible and can be defined precisely, then we have a law. The most precise way of defining something is mathematically. And so law is like a mathematical equation. And so the law that we would generate here is something like this. Like the mass final is equal to the mass or weight initial. Mass and weight are two different things for physicists. For chemists, mass and weight are interchangeable. Do you know the difference between mass and weight? Like, do you weigh the same amount on the moon as you would on Earth? No, actually, you'd weigh like 1/6. Why? Because of the gravity. So weight is going to be affected by gravity. Whereas mass is not. Mass is the amount of matter. And so mass is defined as the quantity of matter. And so the quantity of matter doesn't change whether you're on the Earth or the moon. Like you don't lose half an arm or part of a toe or whatever else. It's going to be the same. So the quantity of matter on the Earth and the moon are the same. And so we have different units for this. Mass is typically in grams or kilograms. And weight is like in pounds or newtons or whatever else. But when was the last time you traveled to the moon? Never. And so that's why chemists use it interchangeably, because chemists, you know, the force of gravity is not going to change from going from the first floor to sixth floor of a building. And so, but technically it's the mass. The quantity of matter didn't change. What happened to the matter? It was just rearranged. And so the amount of matter initial, and so this is kind of the hypothesis, the matter that we had at the beginning is equal to the matter that we have at the end. And so we're taking it one step farther here. And so we have a mathematical equation. And we can write this like mass of final minus the mass of initial is equal to 0. In other words, delta mass is 0. All right, so that's just a law. It's just describing. This is what we call an empirical law. Have you ever heard this word empirical? It's an empirical law. Now, what does empirical refer to? Like, you might have heard the word empirical, like in connection with observation. That's an empirical observation. Empirical means based on observation. So this law is just entirely based on observation. in science, we typically have two types of laws. One is based on observation, it's empirical law. And the other type of observation is based on theory. So we could take our theory, or a theory, I'll talk more about that, and come up with new laws based on this. But we have an empirical law because this law comes from the observations that Lavoisier took. And then this leads to a hypothesis. And we have inklings of the hypothesis here. One of the inklings is this is matter, mass and matter the same. Matter, we define that as anything that occupies space and has mass. And so they're interchangeable in that way. So that's part of the hypothesis. But that's not deep enough, because what is matter made up of? Matter is made up of particles. Yeah, or are they all made up of molecules? No. Because some matter is not made up of molecules, but all matter that chemists study are made up of particles that we call, not molecules are two or more of these. They're made up of atoms. And so matter is made up of atoms. And so what we say is the hypothesis here are that the atoms are rearranged. So I talked about water. Are you going to find water in the sun? You're not going to find water in the sun. What's going to happen? Yeah, the water is going to be torn apart into atoms, hydrogen atoms and oxygen atoms. It used to be H2O molecules. And so the atoms get rearranged. Well, we can have the atoms get rearranged all the time here. And so the atoms were rearranged, but the atoms don't disappear. And so the atoms are neither created nor destroyed. That's another thing that comes from this, another law that comes from this. And then we get the theory. In any kind of chemical, what we call chemical change. Chemical change is related to chemical properties. Chemical properties are chemical reactions. So in any kind of chemical reaction, the atoms get rearranged. In physical processes like melting, boiling, density, the atoms aren't rearranged. And so that's the defining difference between a chemical property and a physical property. Chemical properties, the atoms get rearranged in these chemical reactions. That's why the properties are so different. Okay. And so we come up with a theory, and the theory that comes up is later. This is past Lavoisier. Lavoisier took it to about here. This is Lavoisier. And then there's one other major scientist named Dalton. But actually, this came before Dalton. This predates Dalton, but Dalton put it into the first meaningful. I shouldn't say meaningful, because there were ancient civilizations that also proposed this. And what is it? It's atomic theory, that matter is made up of tiny particles called atoms. So this is atomic theory. So this would be the scientific method here. Lavoisier observed that the masses didn't change, and then that eventually led to atoms with Dalton. Lavoisier is in the 1700s, Dalton's in the 1800s, another century later. And we have something called Dalton's atomic theory. Dalton's atomic theory, even though, yes, as a theory, theories have to be widely accepted, it turned out that some things were wrong in Dalton's atomic theory. And eventually those were caught, and certain things were changed in Dalton's atomic theory. The O in there. So this is the scientific method. So typically it starts off with observation, then goes to patterns. And patterns, not only do we have patterns, but we could also see trends, patterns and trends. And then if those patterns and trends are consistent and well-defined, we can describe those mathematically. And that leads to a deeper. Hypothesis and the theory are a fundamental description of what's going on. Fundamental being at the very base level. And so fundamental descriptions of nature. But a theory has to go one step beyond. A theory needs to do two things. One, it has to be a fundamental description. of the underlying phenomena. And so why do we see no mass change? There's no mass change because the atoms are being rearranged. Now, atomic theory, we have to predict. And so one thing a theory has to do is it has to have the power of prediction. And so now, does atomic theory predict the elixir of life? No. Does it predict the philosopher's stone? No, but it should be able to predict. And this atomic theory can predict new laws such as the law of multiple proportions, etc. We'll talk about that later. New laws and observations. And so based on the theory, what do we predict? Well, and so this is why we have two types of laws. One type of law is a law that's based on observations. That's the empirical, which we'll call 3A. And another type of law is based on theory. I think this one predicted the law of multiple proportions. So what the law of multiple proportions says is that in this, there are a lot of H2O particles called molecules. Can I find one with 3 hydrogens and 1 oxygen? Or is there some chance I might find? Or maybe I might find one with 2.5 hydrogens and 1 oxygen. Or are they all H2Os? It turns out they're all H2Os. That's another law. That's called law of constant composition. The law of constant composition, that didn't come from this. The law that came from this that was predicted is the law of multiple proportions. There might be something with 3 hydrogens, but it would have to have 3. You couldn't have 2.5. And so the law of multiple proportions says that the atoms that make up matter have to combine in simple whole number ratios. So they did find something else that consists of hydrogen and oxygen that forms molecules, and that was hydrogen peroxide. What was hydrogen peroxide? Does anybody know the formula for hydrogen peroxide? The formula is the composition. What's the ratio? Do you know what it is? H2O2. And so this have you heard the joke of this? 2 people walk into a bar. One person says, I'll have an H2O. The bartender gives the H2O. And then that person's friend says, I'll have an H2O2. And so the bartender gives the person H2O2, and that person ends up dying. Have you heard that one? Because H2O2 is hydrogen peroxide, and hydrogen peroxide is poisonous, right? You don't want to drink this stuff. Your body tries to get rid of peroxides and all these other oxidizers. I mean, you have to drink a lot of hydrogen peroxide to kill yourself, but
What is hydrogen peroxide used for?
Used for so many things. Hydrogen peroxide has property in chemistry that it's an oxidizer. And so we can use it to oxidize lots of things, lots of different things. And so some people use it to do laundry with or something like that, try to oxidize the stains out. Other people use it to kill things, because hydrogen peroxide can kill a lot of things. So it used to be that if you had a cut, you'd pour some hydrogen peroxide on it and watch the bubbles and let it oxidize. But they're saying it's too strong of an oxidizer. It's going to cause healthy tissue to become oxidized too, and you don't want to damage the healthy tissue. So don't use hydrogen peroxide anymore. So it used to be recommended as an antiseptic, but I've used tons of this stuff. Like you get a road rash, hydrogen peroxide, and just like bear the pain of the hydrogen peroxide. But now they don't recommend that.
So people use hydrogen peroxide on their laundry?
No, they use it for so many different things. Whenever you need an oxidizer of that strength, hydrogen peroxide is nice because it doesn't give you toxic byproducts. You know what the byproducts of hydrogen peroxide is? If you buy a bottle of hydrogen peroxide, it decomposes into water and oxygen. So water and oxygen, no big deal. And so that's nice. Versus some other oxidizers will have nasty products that you don't want to have around that are toxic or whatnot. So hydrogen peroxide is a good clean oxidizer. But what it's used for is this. If you understand the properties of hydrogen peroxide, you can use it for lots of different things. It's not just used for one thing, it's used for so many different things. In fact, peroxides occur in the body. Our bodies are redox machines. Redox machines are oxidation reduction. We breathe in oxygen, and this goes to burning. We breathe in oxygen, we eat fuel, and we burn the fuel. We don't burn it into a flame, but we burn it. We completely oxidize it. And so we take in the fuel, we oxidize it, we exhale the CO2, that's the byproduct of this oxidation. And so in that process, there's a whole bunch of redox processes happening in the body, and sometimes you make a lot of oxidizers, and you make oxidizers like peroxide. Peroxide's a bad one because that causes damage, but there are other bad ones too, like superoxide. Have you ever heard of superoxide? Superoxide is another one that causes oxidative damage. And so I told you about the supplement that the UC Riverside guy recommends.
Yeah.
And if you're actually, what was his gem? Medcram. Have you ever heard of Medcram? Well, this guy is pretty impressive. This guy is board certified in 5 different specialties. And he started this channel, this education channel. And his name is Dr. Roger Schultz. And he's a professor at Riverside and Loma Linda medical centers. And all his COVID-19 videos are free. The other courses cost money, but he has these specials. But the COVID-19 are all free. And so I watched all of them. And one of the supplements he recommended is this sulfur-containing supplement. But I don't know. Not only did Amazon, because I bought it off Amazon, not only did Amazon drop it, but everybody dropped it. Anything that had some potential benefit for COVID was automatically censored. And what was the reasoning? Well, I can understand the reasoning, but this is a supplement that was taken long before COVID. So if it was taken long before COVID, why all of a sudden now, stop? But he recommended for cold and flu, so that's good, because what it does is it's antioxidant. It has some oxidative damage, and this oxidative damage, he has a hypothesis, and his hypothesis was it causes the blood clotting. And so maybe these will help. Obviously, this is not medical advice, and this is not a medical class, but you want to be open to information, and if he can convince you based on the observations that he sees, then why not? Of course, if you're trained in it, then you would have a better understanding. But this guy's pretty well trained. I mean, 5 board certification 5. But this is a very interesting channel. So there's a lot of videos here on this, but he does a lot of other stuff as well. It's just not this. He has interesting videos on sleep and sleep deprivation, a whole bunch of stuff. So check it out if you're interested. And then he has these paid courses, like if you're coming up for your exams, and these are good for review for those. And so if you know properties, then you can use it for so many different things. You can think of new things to use it for. That's one of the reasons I got into chemistry. Originally I was a geology major, but geologists don't really make things. Geologists observe things, whereas chemists they make things. They can make new things, and in fact, new compounds are being made all the time. For example, talking about properties and stuff. We have, when we think about chemical properties, we have 3 major chemical properties. 3 major chemical properties would be like oxidation reduction, like what's happening in our body, but also what's happening in our body is acid base, the pH of blood. pH of blood, if your blood pH goes too high or too low, that's also potentially fatal. and that type of stuff. So we look and then we try to understand. What we're trying to understand is the properties at a different level. Of course, I can tell you, okay, hydrogen peroxide will react with this. It'll react with this. But do you want to memorize a long list of things it will react with, or do you want to just know? Like, in other words, do you see that chart there on the left? Students have asked me, should I memorize this chart? I said, no. You don't memorize a chart because that would be too much. But you don't completely ignore it either. What you do is you look for patterns. And so this is what scientists do. This is the results of the experiment. So there's your observations. What's the next step in science? In the scientific method, you look for patterns. So that would be the automatic thing I do. I wouldn't memorize each individual observation. I'd look for patterns. And then when you see those patterns, then you can use those. Maybe you'll see a law there. There is a law there I can come up with, but nobody would want to name it because I see a law there because I see this pattern and the pattern is very consistent. And you know what that is? It would be the law of H2O. Actually, this table is kind of small, on the small side. And there's a certain pattern that you see with H2O on some of them, not all of them. You can see. And then there are other things too. There are multiple patterns of that. And so if you know those patterns, then you can do a lot. If you don't know those patterns, all you can do is this. And so I told you that, a lot of exams are like 90% regurgitation. So if you know that chart, you have that chart that's regurgitation. But what if something wasn't on the chart? What if something wasn't on the chart and they put it on the exam? Then you're screwed. You're either screwed because it wasn't on the chart, you don't know, or you would be okay because you know the patterns in the chart. If you know the patterns in the chart, then you can figure out what that something will do. Because, and this is just all part of the scientific method. You go beyond the observation. You don't want to be stuck at the observation. All you can do is use the chart. Anyway, I'm going to, did I forget to record this, or did I record this? Yeah, I recorded. I'm going to stop here because I want to do one last thing in class. How strong of an oxide is hydrogen peroxide? This is a chart of oxide. The strongest oxide on this chart is chlorine, which we call F2. What's number 2 on this chart?
Water.
This is close to water,
Oh,
but don't order this at the bar. Make sure you get H2O, not H2O2. This is hydrogen peroxide. Hydrogen peroxide is a powerful oxide, but it depends on the concentration. There are a whole bunch of factors that influence it. How concentrated is it? You can buy hydrogen peroxide at the supermarket, but it's 5% hydrogen peroxide. If you get like 80%, 90% hydrogen peroxide, watch out because that's potentially explosive. There's one of the professors at UCSB when I was there wanted to get rid of some hydrogen peroxide. And so he came up with the solution to pollution solution. He knows what the hydrogen peroxide is going to decompose to, so he just took some seawater, put it in there, and let it decompose in the seawater. And that's what, and the byproducts are safe, water and oxygen, so you didn't have to worry about anything else. And so it got rid of it that way. But there are lots of different factors that influence these things. And that's what chemistry is. We want to look for these patterns. We want to understand these patterns so we can understand chemistry, because that's basically what chemistry is. And so I know I got to watch out for that stuff, right? Hydrogen peroxide could be pretty nasty. And this is why they're saying don't put it on healthy tissue. But the quizzes for this class, the exams are all closed book, closed notes, that kind of stuff. But the quizzes are